Hey there, and welcome to this explainer. Today, we're going to turn this screen into a virtual science lab. We're going to uncover the hidden secrets of metals, figure out exactly why some materials survive a really heavy beating, while others just completely fall apart, and we're even going to travel back in time to check out a legendary 1600-year-old Indian artifact. Seriously, if you've ever wondered why your pots and pans don't just shatter into a million pieces when you drop them, well, you are absolutely in the right place. Let's get into it.
To kick things off, I want you to just imagine stepping into the scorching, super noisy workshop of an ironsmith named Sudarshan. Picture the glowing coals in the furnace. You can literally feel the intense heat radiating off as he pulls out this red-hot block of iron. He places it on an anvil, raises a massive, heavy hammer, and strikes it hard. Bam! A curious onlooker asks him, "Hey, why are you beating it so aggressively?" And he simply replies, "I am beating it to shape it into an axe." Just think about that for a second. He is hitting a solid piece of matter with incredible force just to change its shape. So why doesn't it just break?
Well, let's dive right into this. That single powerful action, shaping metal with a hammer, is basically the absolute foundation of early human toolmaking. It's exactly how we went from fragile, brittle tools to super durable axes, plows, and swords. And this very concept leads us directly into today's virtual experiment. We're going to test this out for ourselves right now and see exactly how different materials react to a high-impact strike. Okay, so let's set up Activity 4.1 from our textbook right here in our minds. Now, if you were doing this at home or in class, step 1 is always to ensure you have adult supervision. Safety first, right? Next, we need to gather our materials. We're going to grab an iron nail, a piece of copper, a dull lump of coal, and a little pea-sized lump of sulfur. Finally, we just need to find a really solid, hard surface to work on. Got it? Awesome. But wait, before we bring the hammer down on these objects, I want you to put on your scientist hat. A good scientist always makes a prediction before running an experiment. So, what do you think is going to happen when the hammer strikes each of these unique items? Are they going to flatten out like pancake batter, or will they just break into a million little pieces? Take a second and lock in your guesses right now.
All right, let's actually test this out. Imagine swinging that hammer down hard on the lustrous, shiny iron nail. Clang! Okay, now imagine taking that exact same hammer, using the exact same amount of force, and bringing it down on the dull, black piece of coal. Crunch. You know, it's a very different sound, and as we'll see, it's a very different result. Now watch how our raw observations turn into clear scientific data. As we analyze the results from our virtual impact test, a really distinct pattern emerges. Look at the piece of copper and the iron nail. They both have a lustrous or shiny appearance, and when they're hammered, they just flatten right out. But look below that. The lump of sulfur and the piece of coal, well, they're non-lustrous, meaning they look totally dull. And when the hammer hits them, they don't flatten at all. Nope, they just break apart into smaller pieces.
So the crucial point here is how we categorize these materials based on their behavior under pressure. The results are super stark. We have our metals, right, like copper and iron. They're lustrous, they're hard, and they just take the hit, flattening out under the hammer. On the flip side, we have our nonmetals, like the coal and sulfur. They lack that metallic shine, they aren't nearly as structurally hard, and they completely shatter under the exact same pressure. And this brilliantly illustrates the most important scientific term of our explainer today: malleability. Let me repeat that because it's a great word: malleability. It's the specific property that allows most metals to be beaten or rolled into thin sheets without breaking or cracking. It's kind of like a superpower that metals have. When you hit them, their atoms actually slide past one another instead of separating completely. How cool is that?
Now, you might be thinking malleability is just for blacksmiths in heavy, hot workshops, but you've actually seen this property in action in your own everyday life. Ever wrapped up leftovers in aluminum foil? Well, that foil is literally just a piece of aluminum metal that was beaten and rolled incredibly thin, all because it's so incredibly malleable. Or maybe you've been lucky enough to see those fancy Indian sweets decorated with ultra-thin silver foil. It's so thin it basically just melts in your mouth. In fact, out of all the elements out there, gold and silver are actually the most malleable metals known to science.
So now that we deeply understand malleability, we can see exactly why discovering how to work with metals totally revolutionized early civilization. You see, before iron, early civilizations relied really heavily on copper. Copper was much easier to extract from the earth and melt, which made it a fantastic starting point for early toolmakers. But as a metal, it's relatively soft. Once ancient societies, particularly in India, figured out how to build furnaces hot enough to actually extract and shape iron, well, everything changed. Iron is way more durable. The malleability of iron meant a tool wouldn't just shatter the first time it hit a rock in the soil. It literally built the foundation of modern society. And hey, speaking of ancient history, the ultimate proof of India's ancient mastery of shaping iron still stands proudly today, right in Delhi. It's known as the Iron Pillar of Delhi. It was forged during the era of Chandragupta II, which, by the way, was over 1,600 years ago. This thing is massive. It's about 8 meters high and weighs a staggering 6,000 kilograms. But here is the absolute most fascinating fact about it. Despite facing centuries of wind, heavy rainfall, and intense weather, it has barely any rust on it at all. No way, right? It's a true marvel of early metallurgy and a massive testament to how well our ancestors understood the properties of the materials they were shaping.
So, as we wrap up our virtual lab today, I want to leave you with a really quick challenge. Take a look around your own room right now. Seriously, look around. Think about the legs of your desk, the casing of your computer, maybe a paperclip on your table, or even the coins in your pocket. Ask yourself, which of the things around you actually possess the metallic superpower of malleability? And what would happen if, instead, they were made of something that shatters? Keep that scientific curiosity alive, guys, and keep observing the amazing materials that make up our world.